can begin. We are really incredibly lucky to have Shaz with us today. Thanks, Shaz, for accepting our invitation. So, Shaz comes with a rich and still growing legacy of many uh, beautiful and significant research contributions over, I think, more than 2 decades, maybe spanning 2.5 decades, including his work on WIS back in the day, then chess, bounded asynchrony, uh, various sequentialization techniques for concurrent programs, and so on. So a lot of his work has definitely focused on concurrency, but based on techniques drawn from model checking, testing, and the works really. So Shaz was at MSR for a while, and he's currently working in the Novi group in Facebook, which essentially is trying to build large-scale financial services targeting the Libra blockchain. And so he is working on Move, which is the programmable piece of the Libra blockchain. That's one of his projects. And his other current project right now is Civil, which is what he's going to talk about today. So thanks, Shaz. Take it away.
Thank you, Ruksha. Thank you very much for inviting me. It's a real pleasure to come talk to all of you. So I'm gonna, my talk is about reifying concurrent programs. And this is not a typo, it's a real word. So I wanna spend a few moments talking about what I mean by reification, and specifically how it contrasts with the word that you must all be familiar with, which is verification. So verification, you know, it's a program verification. It's a classical project spanning, you know, at least half a century, more than that. And the goal is to, of course, prove properties of programs in a scalable manner. I think of traditional verification as working on a single program representation. And the key to scalability is modularity. So you break your program into pieces, you try to reason about pieces separately, and you set up the reasoning in such a way that what you prove about a piece can be then reused in the context in which that piece is used. This modularity tends to be rather syntactic in nature. Reification, at least the way I think of it, is manipulates not just a single program representation, but it represents the programs, a program at multiple layers of abstraction, and manipulates all of them. These multiple program layers are connected to each other semantically. So their connection imposes a proof obligation, right? Much like proving a property on a program imposes a proof obligation. And this is orthogonal to modularity because multiple program layers are possible even within a single module. As a result, you know, it provides a new dimension to scale automated reasoning, both for a human being who's trying to specify the program, and the computer, which is trying to check that that specification is working as expected. A side point here is that verification, although it's not required, tends to be applied to programs after the fact. So the program is constructed and then we all roll up our sleeves and say, okay, let's try to verify this. It doesn't have to be like this though. Reification, the way I imagine it, is done during program development. But again, you know, that's how I imagine it. It doesn't have to be so. You can always take a program and then try to do verify it using reification after the fact. So another way to think about reification is that it is just, its goal is ultimately the same as verification, which is to build a verified program, but it does that by using more features, more programming features than are typically used in classical verification. So the goal of my work in this area is to build a general purpose language, a modeling language for refining, and with a focus on automated reasoning, to support automated reasoning, all the things that we know and love, SMT solvers, testing, model checking, blah, 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 all that stuff. The kind of questions I'm interested in asking is, are broad, the only unifying theme here is concurrency. So can we say that this implementation of a concurrent garbage collector is correct? Can we say that this implementation of consensus is correct for that failure model? We have an implementation of a cache coherence protocol in hardware. Is that working as expected? So the unifying theme across all this is A, concurrency, and second, an emphasis on bridging the gap between high-level models and low-level implementations. One thing that is an explicit non-goal so far of this work is generating executable code, whether software or hardware, like for example, Verilog, from the low-level reified implementation, right? So far, the goal is simply to be able to represent programs at a low enough level of detail so that you can actually generate efficient executable code from it. But generating executable code will lead to further challenges that are not addressed by this work yet. Any questions so far? Okay, so continuing. So this is how we set up reification for programs. So the first thing to note is that these are structured concurrent programs. So you have, programs P1 to Pn. P1 is the concrete low-level implementation. Pn is the abstract high-level specification. And they are chained together by a formal mathematical notion of refinement. This refinement is very easy to specify. So it's basically preservation of terminating executions. So a program runs, it either terminates fine, right, with some valid state, or it terminates with a failure. What we want in this refinement relationship is that let's compare Pn with Pi plus 1 with Pi, right? So if we say that Pi refines Pi plus 1, that we want that if Pi plus 1 does not fail, then Pi also does not fail. And in that case, every terminating behavior of Pi, final state, is captured by Pi plus 1. So if you chain these things together, this would mean that if you succeed in showing that Pn does not fail, then you have also indirectly succeeded in showing that P1 does not fail. That's all. It's very easy. Now, how are these programs represented? Questions? Did I detect a question? So the programs are represented in a structured fashion. So you have procedures. Procedures can call other procedures. Otherwise, they have all the usual sequencing control flow constructs in them. Two things that are special to concurrent programs are that you can call two procedures in parallel. That's commonly known as structured parallelism. You can also call a procedure asynchronously, meaning that it executes, quote unquote, in a separate thread, right? That's typically referred to as unstructured parallelism. And then finally, there are the state changing operations, the primitives that modify state atomically. And these are represented using this concept of gated atomic actions. So I'll have more details about these gated atomic actions in the next slide, but they are really very expressive primitives to capture arbitrary failures, blocking, and of potentially shared state. Okay. So
I have a question.
Oops, I made a mistake. I hit end as opposed to next here. Was there a question?
Yeah, I had a question.
Yeah, go ahead.
So, this notion of refinement that you have, you might have played around with this, right? So did you consider, for instance, having a more property-focused, property-driven refinement notion? How did you finalize it?
Yeah, that's right. Yeah, so there was a lot of hand-wringing and soul-searching in all this setup, right? And this setup is deliberately chosen to be very simple. So here there is no notion of property. If you want to encode a property, then you have to represent it by introducing variables in your concrete implementation that run along, capturing some partial history of the computation, and then using assertions, okay? So the reason I wanted to stay away from properties is because I wanted to keep the meta theory and then consequently the implementation of this meta theory as simple as possible. And so people can then target it in various different ways. Does that answer your question, Ruksha?
Yes, definitely. Thanks.
Okay. So the next point I want to make is that all these different layers are expressed in a single syntactic unit that we call a layered concurrent program. This is the point I was alluding to earlier when I was motivating reification. So all these layers are represented in one syntactic unit, so that if there's sharing between these layers, we can exploit that. We don't have to do copies, right? So we'll see more of that later. So this civil is implementation of the Boogie tool. So, you know, there's a lot of stuff in there, but at a high level, you can think of it being the implementation organized as follows. You know, you type check the layered concurrent program. If it's well typed, then we can convert the layered concurrent program into a sequential Boogie program. And then we use the normal Boogie verification flow, which creates verification conditions that can be discharged automatically. And we, at this point, we have a ton of experience, not just by the creators of Civil, but other people who have used Civil to verify some programs. Okay. Yeah. Okay, so now let's talk about these gated atomic actions that are the primitives with which these layered concurrent programs are expressed. So semantically, a gated atomic action is a pair, which so there's a gate and a transition. The gate is a single state predicate and transition is two state predicate. So let's look at some examples. So imagine that you have a program with two shared variables, X and Y, okay? Now, if you wanted to express the command X gets X plus Y, its gate would be true, and its transition would be X prime is equal to X plus Y and Y prime is equal to Y, okay? So gate is basically an assertion. So, and blocking has to be expressed inside the transition. Now, let's say that you have the command havoc X. So this puts an arbitrary value into X, but leaves Y unchanged. So this you would express as a gate, which is true, and a transition relation, which says Y prime is equal to Y. You say nothing about X prime, so it can change arbitrarily. Then supposing you have assert X less than Y, that's your command. So in this case, the gate becomes non-trivial. You put X less than Y in the gate, and here the transition is basically skip. It doesn't change the state. So you say X prime equals X and Y prime equals Y. And just to demonstrate that assertions are different from blocking, if you had a command assume X less than Y, notice that its gate is true because it does not have any failures. It only has blocking. And its transition is X less than Y and X prime equals X and Y prime equals Y. Make sense? Any questions?
I do have one question.
Yes, go ahead.
So for a command, like the first one, the transition for X gets X plus Y, is there like an implicit memory frame for variables besides X and Y that if there are,
no, here in this example, there's nothing implicit. That's why I said that the program only contains the variable X and Y.
Got it. So if there were more, there would be additional.
You'll have to have that.
Yeah. Got it. Okay. Thanks.
So,
okay.
Shaz, can you contrast this quickly with guarded commands?
Yeah. So I mean, it comes from there. I would say that if you take out the gate from gated atomic actions, what you have is essentially a guarded command.
I see.
Yeah. So it's a generalization of guarded commands.
Okay.
Yeah. In other words, guarded commands are gated atomic actions whose gate is always true.
Okay.
Yeah. Okay. So now we can write down some real specifications. So let's say that we wanted to express a lock with two operations, acquire and release on it. And we wanted to express the locking protocol, which will include the ID of the thread that's currently holding the lock. So we can write acquire and release as you can see there. So here the blue parts are going to be compiled to the transition relation, and the red part is going to be compiled to the gate. Okay, I'm not going to repeat it. If you don't understand it, just ask me. I think it's pretty easy to understand. Okay. Now there is this other thing called compare and swap. It is another primitive that is often used in concurrent programming. So its specification is here. So I'm implementing a compare and swap on a Boolean variable. So Cas takes an old value of the variable, a new value of the variable, and returns a flag, which is true or false. So here you are doing an atomic action in which you put into S the result of comparing old with B, and then you update B to the new value if the old value matches the current value of B, right? So here I'm using brackets, square brackets, to scope a bunch of stuff, potentially complicated stuff that can execute atomically. Okay, so even though you see there's a semicolon in the middle of these atomic brackets, the whole thing is executing atomically. Okay? So it's very important to internalize this notation for writing gated atomic actions because I'll be using this in the rest of the talk. Questions about it? Okay, so going back to Rupsha's question, why do we have this gated atomic action? Why did we feel the need to generalize guarded commands, classic? It's because what we really wanted to do was to model compactly, as a summary, all behaviors of yield-free code. By yield-free, I mean code without interference, like sequential code. Now this code may contain failures also. And because we want to verify absence of failures in a layered manner, not all of it together, but gradually over layers, we may want to summarize code that has failures in it. To do that, we have to introduce the notion of gates. Okay, so it's a very useful primitive for modeling concurrent programs, either at a concrete level or abstract level. You can model, weak memory models using this. You can also model, high-level consensus specifications using this.
Hi, Shaz, just a quick question.
Yeah.
So is there a particular reason why you separated or you defined acquire separately from Cas? That is, you could have implemented acquire using Cas, right? That is simply—
That's correct. So, but the thing is, as you will see in my example, you can implement acquire using Cas, but when you are reasoning about clients of acquire, you actually want to use the definition of acquire, not the Cas. So you can think of the definition of acquire and release as abstractions of an implementation that will actually use Cas.
So your refinement methodology could, for example,
Yes.
have defined a low-level methodology in terms of Cas, and then prove essentially that acquire is equivalent to that, right?
Absolutely. So the next example has that.
Yep.
Questions? Any other questions? Okay. So here's an example that will illustrate the method, the layered reification method. So we have a program with two shared variables, X and B. So B is the variable on which I'm going to do Cas. I'm going to use B to implement the lock. And X is going to be this counter, which is going to be lock protected, on which I'm going to do a lock protected increment. So the code is split into these procedures, 5 different procedures. Increment, which is in the second column, then acquire and release in the third column, and then reading and writing the variable x in the last column. The brackets, the parentheses look a little bit funny. They're funny only because I intend to do some animation there, okay? So ignore the funny parentheses. Let's take a closer look here at some of the syntax for expressing the code. So you will see two kinds of invocations, call and exec. So I'll follow the convention that call is applied to procedures and exec is applied to atomic actions, okay? And procedures are all named here. Atomic actions are typically named, but here, just for brevity, there are 3 anonymous atomic actions also. So in the last column, do you guys see my mouse?
Yes.
Okay, in the last column, you see this atomic action, V gets X, it's an anonymous action, I'm just executing it. Same here, okay? And then another point to notice is that the procedure acquire is recursive. I could have written it with a loop also, but just again for brevity here. One point about the operational semantics here. So clearly atomic actions execute without interruption, but it is worthwhile pointing out that where interruptions or context switches are allowed. So context switches can happen at beginning and end of procedure calls. Okay, so here inside increment, you know, there is a context switch before acquire, after acquire, before read, after read, and so on and so forth. Okay, and informally, the goal of verification is to show that the clients of Inc can pretend that atomically incremented, and they don't have to worry about all these shenanigans around locking and locked reads and locked writes. Questions so far? Okay, so our strategy is going to be to first convert acquire and release into atomic operations. Okay, create abstractions of them. So this is what my abstraction of acquire and release looks like. So it's defined in terms of a shared variable L, which contains the thread holding the lock, as opposed to this Boolean variable B. Okay, so this is the definition of acquire and release that I showed you on the previous slide. And I have made them all in caps, the names, to distinguish them from the procedures acquire and release. So the atomic actions are, and by convention, will be in caps. So this is, you know, bridging this gap between acquire atomic action and acquire implementation is difficult for several reasons. First of all, the variable representation is different. The actions are represented in terms of this variable L. The implementation is in terms of the variable B. Second thing is that acquire is way more complicated. It has, you know, all sorts of context switches and recursion and all whatnot, whereas the acquire atomic action is just executes atomically. So to bridge this gap, we are going to break things down into little pieces, right? Small things that are easy to justify. And these things that I'm going to introduce into the mix are basically, there are 3 things. We can introduce variables, either global or local. We can hide variables, either global or local. And we can introduce computation on the new variables that have been introduced, okay? So to pull off this magic here of converting acquire procedure into acquire atomic action, I'm going to introduce a global variable L. I'm going to hide the global variable B. And I'm going to introduce local variables throughout the call stack for representing thread IDs. Okay, and I'm going to just thread that thread ID through all the procedure calls. Okay. You'll see this linear annotation on the thread ID variable. It just means that I'm doing some linear typing here to make sure that thread IDs are not duplicated. The exact mechanics of it, you know, there's an entire section towards in a later part of the talk where I go into the details of what that means. So just ignore that and just assume that, you know, 2 threads that are executing, their thread IDs are different. And then finally, we have these introduction actions. So when I introduce L, I have to provide updates to them. So I do the natural thing that you would imagine. So if the cast succeeded, then I set L to the thread ID and inside the release, otherwise I don't do anything to L. And if the release, inside the release, I set L back to none. Okay? Are things clear so far? Okay.
Sorry, just a quick question.
Yeah.
So is your semantics parameterized on the memory model, or are you sort of assuming SC at this point?
SC.
Okay. Because
if you want to encode any memory model, you have to do it yourself by using shared variables and queues and whatnot. And the methodology doesn't, you have to just be in this methodology and try to eliminate the memory model by creating abstractions.
Ah, okay. Okay.
Yeah, that's right. So for example, it is, there are some case studies that, little examples where you try to model weak memory at the lowest layer and then you hide the buffers there. And at the upper layer, you manage to get to basically standard locking operations, things like that.
Right, right. Yeah, we'll talk offline. Yeah, there are other techniques that we've looked at, right? Yeah, exactly.
Okay, so.
Shaz,
I just have,
sorry, was there anybody else?
just, that's me. Hi.
Yeah.
Yeah, then you
Yeah.
go.
Where in the bottom half, where did this L come from that you're doing this intro? Where is that variable bound? Is that like an implicit?
So this variable, yeah, this one is an interesting issue. The variable L is being introduced above the line. You see that?
Yeah.
So one way to think about it is that it's actually, I wrote it there, but really you should think of it as being introduced already below the line, and then it is carried over above the line. So that the variable L is declared, it's a global variable that is declared. It is now introduced at the next layer. Yeah.
Okay.
Just I had a quick question.
Yeah.
So at the lowest level, you're talking about context switches. So are there any assumptions on the scheduler? Like, do you have to assume like or are we just talking about all possible interleavings?
All possible interleavings.
Okay.
So an interleaving can happen at any point a procedure is called. So beginning of acquire procedure, end of acquire procedure, inside the acquire procedure, at that when you have a recursive call to acquire there after it, and so on and so forth. But there is no, this introduction action is again special. When you call atomic actions, there is no context switch before or after an atomic action. Okay? Otherwise, you can pretend that otherwise there's context switches everywhere. Does that answer your question?
Yeah, it does. It does. Thank you so much.
Okay, Rupsha, you had a question?
Yeah. I think mine was more related to Ben's, which is that I think I missed the part about how you infer these introduction actions. How do you deduce?
I did not infer anything. This is all done by the programmer.
Oh, I see. Okay.
Yeah.
Okay.
So the programmer has to do all this.
Mm-hmm.
And then now programmer also has to specify this invariant, which captures the relationship between the freshly introduced variable L and the already existing variable B.
Okay.
Once the programmer has done that, then the tool can automatically check that all behaviors of acquire procedure are like the acquire atomic action, and same for the release procedure against the release atomic action. So once the programmer does that, we can also in addition show that the procedure read can be converted into this atomic action read. Okay. Now one might wonder, why are you doing that? The body of read is already an atomic action. Why are you making that atomic action somewhat richer or more sophisticated by guarding it with this predicate that the lock is held by the thread invoking read? For it makes the locking protocol, the fact that this read and write is done while holding the lock, it makes it local and explicit. And that allows me to soundly rewrite the body of procedure inc as a sequence of 4 atomic action calls to these atomic actions: acquire, read, write, and release. And this is justified. So notice that there's a justification required here, because as I've mentioned, when you are invoking atomic actions, there are no context switches. So just by doing this rewrite, we're actually saying that the body of ink does not have any context switches in the middle. So how do you justify that? It is justified because now we have definitions of these atomic actions and they have certain commutativity types. So for example, acquire is a right mover, release is a left mover, and read and write are both movers. The reason we are able to prove read and write both movers is precisely because of this guard, this gate that we have introduced, expressing the locking protocol. Okay. Now at this point, we're almost done. We have to convert ink, whose body is now atomic, into an atomic action. And we can now hide the lock variable. So at the upper layer, we can now hide the lock variable. We can hide the parameter tid, which is passed to ink. And now we have an atomic action increment that just increments x by 1. Okay. Questions?
I do have one more question.
Yeah.
What's the right way to read these boxes? Are these just explanations, like the rewritten calls and the introduced local? Are those explanations, or is that some information that the user has to provide to the verifier?
No, this is just my explanation.
Okay,
what the programmer writes is just what you're seeing in black.
Okay.
Yeah.
So this right mover, left mover thing, that's just.
No, the right mover, left mover is also written. Let me actually show you what the programmer writes. This is what the programmer will write.
Thanks.
So as I was saying, all these layers are expressed as one piece of syntax. So this is what that piece of syntax is. So here, you'll see that you have variable declarations, shared variable declarations, as well as local variable declarations. You have declarations of atomic actions. You have declarations of procedures. And you also have the specification of these mover types. So you see on acquire in the middle box, you see write. So write means that, okay, it's an atomic action, and we are saying that it has a commutativity type, it's a right mover. On the other hand, in the left box, when you see Qaz, it says atomic. So we are saying it's an atomic action, but it does not commute. Okay?
Why would a user need to provide the mover type? Isn't this something that can be easily inferred? Isn't this mostly standard?
No, how is it, which part is standard?
The mover types. I mean, we know that certain kinds of statements and certain kinds of synchronization are right movers or left movers.
No, but that's not true, Rupsha. I mean, think about it this way. Supposing this atomic action read, I did not put this gate here. And we did V gets X. That is not a mover. It conflicts with this other one, right?
Right.
So, I mean, actually, it's a very sophisticated thing to know whether to make an action commute. Sometimes you have to set up the atomic actions just right for them to start commuting. And so, I mean, if you don't check it, if you don't check the programmer's work, the programmer could easily make a mistake. So you asked actually two different questions. The first question that you asked was, aren't mover types trivial? So I think I have said the answer is no, they're not trivial. But you asked a second question, can they be automatically inferred given a certain set of atomic actions? And the answer is yes, they can, because it's a finite thing. There's only 3 mover types possible, 4 mover types: atomic, right, left, and both, right? So if I have n atomic actions, I have 4 to the n combinations. I can try out all those combinations and I can do my checking about mover types for all those combinations, right? I can do that. And I can possibly get smarter than that also. All of that is possible, but not yet. One thing at a time. You see what I mean?
Yes.
Okay. All right. So the other thing I want you to see here is that there are these funny at layer annotations, etc. So these are the things that distinguish a layered concurrent program from an ordinary concurrent program. Because this is what is allowing you to represent multiple layers of a program while doing maximal amount of sharing. So for example, if you look at this procedure, inc at 2, at 2 means that this procedure, the last layer at which this procedure exists is layer 2. So it exists at all layers below 2, at 1, at 0 also. But we didn't have to make code copies for representing the body of ink at those lower layers. I just represented them like this. So these layer annotations have to be type checked to be consistent. So for example, it would be wrong for an atomic action. So here's an atomic action, right? 1, 1. This is saying that this atomic action exists in this layer range. In this case, the layer range happens to be just a singleton containing 1. So given an atomic action with a specified layer range, it would be wrong for that atomic action to access a global variable that is not available in that entire layer range. So global variables also have a layer range at which they exist. So they are introduced and then they are hidden, right? Local variables also have layer ranges. They're introduced and they're hidden. So there's basically, like a whole bunch of type checking that has to be done to make sure that these layer annotations are consistent. And if they're consistent, then you can actually split this program into, these 3 programs that I showed you here. Okay. All right. So that's all I want to say about this particular slide. Any questions about it? Okay. Now let's go into more detail about what happens once the program type checks, the layered concurrent program type checks. So if it type checks, then we know that there are all these layers from P0 up to some Pn. And we have to check that this refinement relationship between adjacent layers. So it is done basically layer by layer. So internally, what the tool will do is do this checking for each pair of connected layers, Pi to Pi plus 1. So the first thing that happens is that you go from, you first analyze the program using all this commutativity information to say that, okay, the preemptive semantics of Pi is equivalent to the cooperative semantics on Pi. So by preemptive, I mean, okay, well, there are context switches everywhere. Cooperative means that, no, there are not context switches everywhere. They're only at the special locations. And to do that, you have to check that the commutativity types are correct. And then you also have to check that these yield to yield code fragments inside procedures, they satisfy this regular expression, that they look like a sequence of right movers followed by at most one non-mover followed by a sequence of left movers. Okay. So you can do this, you can basically compile this into a classical simulation check, right? So I implemented one of those, good old simulation relation algorithms for doing this, but there are many ways of pulling this off. So as an example, to prove the preemptive to cooperative semantics on this body of increment, I had to show that, this code block here looks like right movers followed by left movers, which it does. And in addition, I had to check all these mover types for acquire, release, read, and write. Okay, once we have done that, now we are going to do reason about the cooperative semantics on Pi. So we instrument Pi with the introduced state, right? So in this case, we introduce all the local variables and the global variables that are introduced at layer I. and the code, the introduction code that is providing assignments to those freshly introduced variables. Then, so this program is what we call PI tilde. So this is like a middle program between PI and PI plus 1. Now we modularly check. So what will happen is that there are some procedures that are going to disappear at layer I plus 1. So these are the procedures whose the last layer at which they exist is I. So because they disappear, they're going to be abstracted by atomic actions. For each such procedure P, that is summarized by an atomic action A, we have to do this modular checking that it behaves, the body of P behaves like A. So for that, we require the programmer provide some context using invariants. And how to do invariants is its own story. And then using the context provided by those invariants, you have to then show that every execution through P behaves like skip star A skip star. So skip is the atomic action that does nothing, does not have any visible side effect. And A is the atomic action that is the summary of P. So you basically have to show that along every path, every execution through P, the atomic action happens once and exactly once. So inside for the proof on acquire, it will have a sequence of failing cases followed by exactly once cas. And so by using the invariant, we will be able to show that the failing cases are simulated by skip and the successful cas is simulated by acquire. Okay. Then the final step to get to PI plus 1 is that we replace calls to P with calls to A, right? We drop all procedures P that become dead code now. We drop all the state that has been hidden, and then we get to PI plus 1. Okay. All right. So any questions so far? Okay.
Hi, Shaz, just a quick question.
Yeah.
So when we have, I'm just trying to get an understanding of the methodology that you're employing. So typically when you have highly concurrent lock-free algorithms, the challenge is establishing these invariants, making these invariants inductive over all possible interleavings. So if I were to make a mistake and I incorrectly made a block, I should have made a block a larger atomic unit than, and I didn't, my proof will fail, right? There will be some point where I would have seen something that breaks the invariant. I'm trying to get a sense from you about what the methodology you would employ given that failure to actually identify the sort of context block that you want to.
Very good. Excellent. Excellent. So notice that when you use this tool and its methodology, you get warnings and error messages from a variety of sources. So for example, the simplest kind of things that are easiest to fix are these layer type checking, so not surprising. But then, for example, when you put these commutativity annotations, you can get a complaint there. You may say, okay, you're claiming that this action is right mover, but given the pool of atomic actions at a particular layer, I cannot prove that it is right mover based on the logical reasoning that it is doing. So you get very localized, focused error messages. So then you go try to fix that commutativity problem. Once you have passed all the commutativity problems, you can get error messages that, okay, well, I mean, you put a yield here and here in the middle, you actually have a left mover followed by a right mover. So then you go and fix that. Once you're done with all that, then you move to the actual invariant checking phase. And then you will start getting error messages based on, hey, I'm unable to prove that this invariant you wrote is interference free because this particular code fragment in a different thread does not preserve it. Then you go debug that. You may also get error messages saying that, okay, assuming all these invariants are correct, I'm not able to prove this refinement check against the atomic action. So the error messages the tool spits out at you, they're very focused. So you know what specifically the issue is. Does that answer your question?
Yeah, sort of. I think so. I guess the sort of follow-on is that sometimes because the tool is sort of defining as some over approximation over the actual behaviors that actually occur, you may want to inject asserts or some other, for example, commutativity violations can often be benign, right? It doesn't matter. It is true that there's a violation, but maybe this doesn't actually matter because these violations occur inside of a failed CAS path, right? It's not going to actually show up.
So I mean, exactly, I actually showed you a very simple example of that. So intuitively, you know that this exec, this read and this write commutes. Why? Because you know that you're holding the lock. There's some contextual information. But if you try to put the mover annotation at this atomic action here, that it's a right mover, the tool will say, no, I can't prove it. That's why you had to convert this, you had to abstract this atomic action into this atomic action. And you explicitly had to provide as an assertion the contextual information that will now allow the tool to prove locally that this thing is a commuting operation. Right. So this is actually also very common what you're saying, that you sometimes have to create a layer just to transform atomic actions into something which have the right commutativity properties.
Yeah, exactly. Right up. Very good. Thank you.
Okay, so any more questions about this one? Because now I'm going to jump to a different piece, right? The issue about invariance, which is its own thing, because it's like the workhorse of all this reasoning that we have to address. You can also think of invariance as the, what is it, the white elephant, pink elephant? One of those elephants, you know, that nobody wants to acknowledge. Okay, so as I was indicating earlier, that to do the final step of the transformation from PI to PI plus 1, you typically need to supply invariants. The invariants may be needed either because you are discharging some of the failures at layer PI, so those failures are missing in PI plus 1, so you have to justify why they are missing. Or it could be because you are transforming the state in some way to enable further reasoning at PI plus 1. No, in that case also you have to supply invariants. So invariants are really the workhorse of any kind of deductive verifier, and Civil is a deductive verifier. So we have a treatment of invariants, and the treatment that we have is independently interesting also. Even if you are just doing one-shot verification and are not interested in doing layered proofs, you may find something of value in the way we treat invariants. So, okay, so here's a very quick history of invariants. So the most classical treatment that I'm familiar with is done on transition systems. So you have a set of initial states and then you have a transition relation, and you prove, you talk about an inductive invariant, which is implied by the initial state. It is preserved by the transition relation, and it is disjoint with the set of error states, okay? Typically, programs are not composed as transition systems. They're composed with more structure. So people have made an attempt to add invariants to that structure. So you have a more structured representation of invariants. The earliest such attempt that I am familiar with is by Floyd, and actually there might be something predating this by Turing, who put invariants on flow graphs, right, flow charts. Later on, Floyd's method was popularized by Tony Hoare, where he, instead of flow graphs, he described the method on structured programs. But that was for sequential programs. There was no concurrency there. And in the 70s and 80s, this work of Floyd and Hoare was generalized to structured programs, structured concurrent programs, separately by Owicki Grease and Cliff Jones. Owicki Grease are two different people, Susan Owicki and David Grease. So the crux of, so I want to focus on invariants for concurrent programs. Okay, so the crux of the issue here is specifying non-interference, okay? And this is what it boils down to. Imagine that you have a program with global state G, and there's a thread that is running, and it has its own local state L. So it executes some piece of code, and then there's a yield point. Now, interference can happen here, and then it resumes with the piece of code C2. So the question typically is, what state changes are allowed here at the yield? So the simplest thing you can say is that, well, I mean, G, which is the only thing that a different thread can modify, can be arbitrarily havocked here. That will typically not work. It's too coarse. So you have to say a little bit more here. And this is the hardest thing about dealing with concurrent programs in a deductive style, which is you have to specify something that is established by that thread and is preserved by arbitrary execution, arbitrary interference by the other threads. So what Wakey and Rees did, I call their work, I refer to their solution as location invariance. So they say that, okay, well, decorate yield with a predicate phi that could refer to any variable in scope. Specifically, it can refer to L and or G. And this predicate must be interference free. So there's a proof obligation which must show that, yield-free code fragments executed by other threads preserve this. And of course, the calling thread must set it up when it reaches the control point. So this is very precise, but it's quite verbose because you may have to repeat marginally different location invariants at lots of control points. So Cliff Jones came up with a nice thing called rely conditions. So he said that, okay, well, it could be that in many cases, a piece of code with many yield points inside it, that all the interference that that code is suffering from can be captured by a rely condition, which relates how the global state can change at any yield point inside that code fragment. And you can separate that out and write it in one place as a rely condition that relates G with G prime. So G is the state before the interference and G prime is the state after the interference, okay? So this is very nice when it works because it's compact, but it is imprecise, and not just because it tries to approximate over all interference that can happen over a piece of code, but more importantly, because it is not context dependent. See, the local variable doesn't appear in place here. And many, many times, what you want is some relationship between some local variable and the global state to be unalterable, to be unchanged. So doing context dependent reasoning becomes very difficult if you rely entirely on these rely conditions. So I would say that they're compact when it works, but it is imprecise. So in the civil verifier, we have introduced a technique called yield invariance that is, in my opinion, both precise and compact because it's able to basically somehow unify location invariance and rely conditions in one way. So you get the nice attributes of both, okay? One point that I want to make is that these things are methodologically very important because you are asking the programmer to supply them, but they're also computationally very important, whether you are checking them or inferring them, because the complexity of verification, and inference is going to be strictly higher than that, is proportional to the size of the program roughly, and the number of such assertions that you have written, just extra assertions, location invariance, rely conditions, or yield invariance. So if, for example, one reason why location invariants are so expensive for the computer is because you may be writing a number of location invariants that is proportional to the size of the program. So your checking now becomes quadratic in the size of the program. Okay. Any questions so far?
So I just had a quick question.
Yes.
Does separation logic also fall in this matrix of method of specifying what can go wrong at what is allowed at the yield points, or is that like a separate thing altogether?
In my opinion, separation logic is a separate thing altogether. I think that the way I think of separation logic is that it is essentially about a custom way of eliminating non-interference, which allows them to get certain code blocks naturally atomic, but it is very rigid. So it is not nearly as flexible as these techniques, which are explicitly based on specifying logical conditions to get interference in general situations, okay?
That makes sense. Thank you.
So separation logic, I think, is fairly rigid, and it is mostly dealing with memory-based separation, where you really have disjoint pieces of memory. So one thread owns one piece of memory, you have to somehow capture that. Another thread is messing around with something else. Things that are based on predicates and not on complete disjoint separation, you basically need something like this. So, as a result, separation logic tends to be applied to shared memory algorithm, and specifically to shared memory algorithms that are using locks in a very, very disciplined way. They're using coarse-grained locks, and your invariants don't span multiple lock critical sections and so on. For if you're dealing with message passing concurrency, or if you're doing fine-grained locking, or if you're doing system level invariants of concurrent programs, separation logic needs to be augmented by things like this. Any other question?
Shaz just wanted to interrupt and say we have 1 minute to 1 o'clock. So maybe we can hold off questions now till the end. So if some people need to leave, they can leave after Shaz finishes his talk. Okay.
That sounds good. Okay. So let's go to yield invariants. So yield invariants are named and parameterized. Okay. So named means that you can declare them independently and check them to be free of non-interference. Okay. And parameterized means that they have to be called, they have to be invoked, so you can specialize them to the calling context. So in a way, they are putting together the good properties of both the work of Wikigrease and Cliff Jones. So here's a yield invariant. It expresses this fact that the shared variable X is at least as large as the input I to the yield invariant. So I want to show you now how to use this yield invariant to show that this, to demonstrate this, that this procedure double link increments X at least twice, okay? So there could be a context switch at the beginning, in the middle of those two atomic increments, and at the end, okay? So what we are going to do is we're going to use that one yield invariant, but we're going to invoke it with different values to get the effect that we want. So at the yield point, at procedure entry, I invoke the yield invariant with old X. So think of old X as the value at the call site of double link, the value of X at that point, okay, at entry. Then and then in the middle, I'm going to invoke it with the current value of X, and at the end, I'm going to invoke it with old X plus 2. So let's look at what the reasoning mechanism is, the way even the computer or the human being would reason about it. So at the beginning, we have to establish that, let's say that X0 is the value, is the incarnation of X before the call. So the caller has to establish that X0 is greater than or equal to X0. So I basically grabbed the invariant and I substituted the incarnation X0 for X and the value that I am passing for the parameter I for I, okay? So that clearly holds, right? And that X0 is greater than or equal to X0. So then we have a yield to simulate that we create a new incarnation of X, X1, and we get to assume the invariant again. Why do we get to assume it? Because we are assuming that separately we have verified that the yield invariant is interference free. So we assume X1 is greater than or equal to X0. Then we have the increment of X, and then we have to establish the invariant again. So we are calling it at the incarnation X2. Establishing it is just fine. Then there's again a yield. So we get the third incarnation X3 and so on. And then we make the second call. And so you can see if you chain all of these facts together, you'll see that you would have established all the assertions and you get the assumption at the end, which the caller can exploit. Okay. The first version the earliest version of Civil was based on a Wikigrease location invariance. After we introduced yield invariance, we decided to look at how much benefit we get. So we ported our largest examples from location invariance to yield invariance, and the benefit is dramatic. So you get reuse, which is what you would expect, up to a factor of 13, depends on the examples. Performance-wise, we are actually able to demonstrate on an artificial parametric example this quadratic to linear improvement. And some of the two most, the largest examples that we have, which is an implementation of the verified FT, fast track race detector, we got up to, the running time became half. And, on the garbage collector, the concurrent garbage collector, the running time became significantly smaller. Okay. So I'm now going to talk about non-interference, Rupsha. I have like 4 more slides, plus some concluding slides. Do we want to allow, should I continue or?
I think we should try to wrap up quickly. So if you can just pick some stuff that you want to highlight in the remaining slides.
Okay, so then I think I will skip this section about non-interference. This section is about how we use linearity, linear typing, and combine it with logical reasoning to make non-interference checking easy and flexible. So this is done, basically we have a way using linear typing and logical reasoning, we have a way to encode permissions, which gives us the kind of effect that separation logic, for example, shoots for, but in a more general setting, okay? So you can do the kinds of things that separation logic does, which is based on separation of memory, but turns out that this more general setup of combining linear typing with logical reasoning is useful in many other situations, including verification of consensus protocols, message passing systems. So I'll skip over all that. We can go over those things in our one-ones if you are interested. What I'll do now is just conclude. So what I've been telling you about is an approach called program reification via program layers. You can think of it as a technique for constructing verified programs. And I use the word constructing very deliberately here. I really think that, I really don't think that functional verification of programs is going to succeed after the fact. You have to do it while you're doing program development. The focus here is connecting abstract models to concrete implementations. One very important attribute of this method is that it is extensible. So once you have many layers, you can imagine different verification techniques that allow you to connect 2 different layers. And this makes the whole system extensible with new verification techniques that are suitable, that are domain specific, that are suitable for a particular kind of verification problem. Some concluding remarks. So, what I've learned is not just because of my work on civil, but in general, over the past, 10 years or so, putting verification into production is hard. And the reason is that there's a big gap between general purpose automated reasoning techniques and the kind of tool chains you must build to help programmers who are interested in verified programming. So there's a huge amount of work that must be done to specialize general purpose automated reasoning technique. This is very creative and challenging work. This is akin to almost, how should I say, language design, right? Compiler tool chains and so on and so forth. But I think that that work must be done. Some of it is already being done. And as these things, verification techniques become more commonplace, as people realize that they can actually be used to solve practical problems, I think that we'll see emergence of domain-specific languages, tools, and frameworks that will enable construction of verified programs in critical application domains. So I think that's why we're at an exciting time here. I think that the next 10, 15 years is going to be very exciting in the area of program verification. That's all.
Thanks, Shaz. Maybe we can all unmute and give Shaz a round of applause, or you can, use your applause thing. Okay. Thanks, Shaz, for that amazing talk. we can now open up the floor and use it for questions or revisiting some slides or some missing slides.
Yeah.
So any more questions or comments?
I was curious about the use of linear typing to encode permissions. What does it simplify in the reasoning for that those access patterns?
So Ruksha, at this point, is it reasonable to go back to those slides and then show them the slides? Show the slides?
Sure.
Okay. So I will. So non-interference is hard. That's the motivation. So to explain that, let me look at this. Let's look at this very simple example. Imagine that we have a barrier implementation. And in fact, this barrier implementation is culled. It was used in a piece of the concurrent garbage collector that I developed together with Iris Petrang, Chris Hoblitzel. Was the first program that we verified with Civil. So here, there are mutators that enter the barrier and then exit the barrier. So the barrier is modeled as a set of thread IDs, right? So when you enter the barrier, you add the thread ID of the calling thread to the barrier set. When you exit the barrier, you remove the thread ID from the barrier set. So imagine that for some reason, we want in the middle of the barrier, when the mutator has entered but not exited, to know that the thread ID belongs to the barrier set, okay? So this fact is hard to prove that it is interference-free. Because to prove it interference-free, you will have to definitely show that if the mutator invariant holds for thread J, where J is the parameter to mutator invariant, and a concurrently executing thread calls exit barrier with the value I, then mutator invariant still holds, right? For J. But this is not provable because I could be the same as J. We just know that some other thread is calling exit barrier. We don't know any information about the values that were passed to the mutator invariant and to the exit barrier by these two threads. So we won't be able to prove this. So linear typing and logical reasoning helps us here. So, I mean, before we go there, right, why can't we get around this by writing some more invariants? Well, the problem is that the invariants have to be well scoped. At the global level, you can't say that I and J are different because you don't have access to local variables at the global scope. You also can't write this the fact that I and J are different in the scope of a particular procedure because you are referring to two different scopes, okay? So what we do here is that we solve the problem using linear typing and logical reasoning. So we declare that the parameters to mutator invariant, enter barrier, and exit barrier are linear. And we use a linear type system to make sure that these values are never duplicated. So the linear type system makes sure that, it gives us this very strong guarantee that at runtime, if you have two different stack frames, for example, of two different threads, the value of the variable I in those two different locations is going to be distinct, okay? And as a result, because that fact has been given to us by the linear typing, when we are doing this non-interference check, we can get that as a free assume. So we can inject that as an assume in the verification condition that I is different from J. And that will allow us to prove this. Okay, so this is the very simplest combination of linear typing and logical reasoning that you can do. But unfortunately, distinct values are not enough. So if we take a closer look at the garbage collector, well, I mean, in addition to the mutators, there's going to be a collector also. And the collector is the one who wanted the mutators to enter the barrier. So what the collector will do in its code is that it's going to wait until the barrier has succeeded. So it will execute this weight barrier atomic action, right? And weight barrier is saying, well, assume, wait until the barrier set contains all the thread IDs of all the mutators. And then at that point, it's going to do some very critical operation for which it needs to know that all the mutators are inside the barrier and not messing around with memory, right? So it might be, for example, doing a root scan. So, I mean, to really pull this off, we have to now make sure that the collector invariant, which was established right after by the collector right after the weight barrier, is interference free, right? So you will have to show that collector invariant holds when exit barrier is invoked by a different thread. We can't do that, right? Again, because we don't know, I mean, well, that this exit barrier is not possible to be executed here. So the thing is that yeah, why is it not allowed to be executed? I think it's because there is some other synchronization that is missing here that I'm not showing you. Okay, so ignore the fact. I mean, the thing is that the way I've shown this code, once the mutator has entered the barrier, it can just execute the exit barrier and falsify this. But actually, that does not happen. There's a whole bunch of code that is missing here. Just, I mean, I've eliminated all that just so I can make my point. Okay, so here we can do a more advanced use of linear typing and logical reasoning, where we generalize from distinct values to disjoint permissions. Okay, so here the idea is that the linear typing works just as before, where it makes sure that linear variables are not duplicated. But the semantic guarantee that we get from that in terms of values is generalized. So what we do is we associate sets of permissions with linear variables. And the invariant that we maintain is that those sets are all disjoint from each other, okay? So the set of values associated with the concrete program value is called a permission, and we're going to make sure that these permission sets are disjoint. So in this case, now we can make the barrier set linear. Okay, so it is a thread of IDs, and we can say we can create a permission type which contains the left half of a thread ID and the right half of the thread ID. And then we can say that when the thread is put into the barrier, it takes only the left half with itself. So the typical pattern is going to be that when the mutator has both halves of its thread ID with it, when it enters the barrier, it gives the left half to the barrier set and keeps the right half itself. It presents the right half to the mutator invariant. And when it exits the barrier, it gives the right half that it has back to exit barrier. It removes the left half from the permission set, from the barrier set, puts the two together and returns the ID back. And now it has the whole ID again, so it can go through this process again. So if we implement this kind of protocol, we can now show that mutator invariant is preserved by exit barrier, because we know the permissions that are coming into mutator invariant include the right half of I, which is the same. And here the permission that is coming into exit barrier is right half of I. Because the two permission sets, we can freely put an assumption that the two permission sets are disjoint. We will know that at the point where the mutator calls mutator invariant, a concurrent exit barrier on the same I cannot be executed. So we'll be able to prove non-interference. That was the story.
Thanks.
I hope it kind of made sense.
It did. It did kind of make sense.
Okay. More questions?
Students, this is your opportunity to ask questions of Shaz.
Well, if the floor is still open, I was wondering if you've looked at ways for kind of helping the programmer write all these different layers that are needed in the reification. Because it seems like if I'm writing a program with these layers to help connect the concrete implementation to the specification, I'm going to end up writing a lot more syntactically than I would just writing some program that doesn't have these guarantees. Have you looked at ways for maybe being able to infer some of those intermediate layers, or at least make it simpler to write them?
Yeah. Well, so my experience suggests that writing the layers is not the hardest part.
When you say your experience, do you mean you or you?
So you by that, I think that what you're asking is about the level of expertise with verification techniques, right?
Yes.
So, I mean, I'm going to be very honest with you. All of this, I mean, even, okay, so how do I even say it? Just because I'm working on verification of concurrent programs and I'm writing conference papers on that, doesn't mean that verification of sequential programs is a solved problem, right? So, I mean, right now, programmers can't even write verified sequential programs. So this thing that we are talking about is like way out there, right? So we are nowhere close to helping any real programmer despite my 10 years of work on civil. And I guarantee you that if I continue working on civil for the next 10 years, I don't think that the situation would have dramatically changed. Okay. So the question that I can, so I think that, but I know the angst that you are feeling, which is that there's a lot of work here and it's really bothersome. How do I make it easy? I think that the principled way, so given that we're not going to be able to help anybody tomorrow, this is going to be a sustained effort, 10, 15, 20 years, you know, okay, I hope, you know, before I die, right? So let's say 10 years, right? How do you prioritize what things you should try to infer and what things you should just ask the programmer to provide and educate the programmers in new things? Education is possible, right? I mean, if you look at programming paradigms, they have changed. It takes time, but things do change. So today, for example, young kids, they're programming in Rust, right? That's a very crazy language. There's a lot of functional gobbledygook floating around in here, you know, with some type theory. But, you know, for a kid who has never seen C or who has never seen JavaScript, they might as well learn that, you know? Okay, so getting off the soapbox and getting down to practical issues, the question is, given all the challenges, what are the first things that you should try to automate in this whole thing? So I can give you my subjective opinion in here. So I think that the most annoying part of doing a civil proof is the non-creative part. Coming up with the layers is creative, okay? And I think that because it is creative, it's going to be hard to make it automatically inferable in a robust way. But there's a lot of boilerplate shit that goes on in doing a civil proof. One of them is the propagation of invariants. So when you do proofs with invariants, there is the creative part of coming up with the invariant, the inside of the invariant. And then there's all this propagation up and down the call stack that you have to do, where you have to write slightly different versions of invariants. Maybe you have to instantiate the invariant with different parameters and so on. Maybe you have to add a few other things. That is very tedious. I would focus on that. if you're interested in really in developing new program verification machinery and specifically automation, I would focus on that. If you're interested in more in programming languages and compilers, I would suggest just bear with it, right? You want to crank out papers, right? When you see people are cranking out papers, writing Coq proofs and whatnot, right? So it's perfectly respectable. You can write papers. So what I would then advise you to do, if you're interested in programming languages and compilers, then you take this and you try to figure out, well, how can I build a programming language out of this where you can do these layered proofs, but you can still get executable code out of it. I guarantee you, even in the current state of affairs, if you do this, you'll be way better off than the guys who are doing Coq proofs, right? Why? Because even though you have not made it accessible to an ordinary programmer, you have still specialized a lot to what typical programs look like. And you would have made a very valuable contribution if you did that. You see what I mean?
Yeah.
Yeah.
Great, thanks. Yeah, that makes sense. That trying to solve the last problem should always come after solving an achievable problem.
Yes, yes, yes.
So anybody here in the audience wants to challenge Shaz on that?
On what?
On his opinion about papers with Coq proofs?
I mean,
Yeah, I have a half an hour to challenge him, so I'll do that then. But yeah, he won't get away with it. So.
I mean, the thing is that I love Coq proofs. I love all kinds of proofs. But I mean, I think it's a little presumptuous to say that just because I can do some Coq proofs, or just because, I can do some proof of a garbage collector using my fancy new thing called Civil, suddenly we have solved some problems, No, we haven't solved any problems. We just have learned something. Yes. Maybe it will solve some problems later.
Okay, so maybe we can actually wrap up by, Shaz, did you want to say something to all the students here? Some philosophy that they could.
Well, I will just recapitulate something that I think is attributed to Leslie Lamport. Which I read in some interview published on the web. He said that, you should stop listening to old farts and just go do your thing. So that is very good, I mean, I think we spend too much time listening to all these people, typically at conferences, etc., about what is and is not doable and what are the right ways about how to make progress and so on. You just figure out, what problem you want to work on, and you chart your own path.
All right. So on that note, let's thank Shaz again and maybe give him a couple of minutes to take a break before a series of meetings.
All right. Thank
Shaz.
you all. Wonderful questions, by the way. I really like it when people ask lots of questions. Thank you so much for attending my talk. Bye.
Bye.